This video will cover the ideal gas law, its application, trends, and possible deviations from the law. Let's start with a very simple question. How do gases behave? Actually, this is one of the hardest questions imaginable. How are you supposed to observe the behavior of something you can't even see? Luckily, some brilliant chemists already figured it out, so we can rest easy. It first started with Robert Boyle in the 1600s. He found an interesting relationship between the pressure of a gas and its volume. Specifically, he discovered that as the volume of a gas increased, its pressure decreased, and that this happened in a 1-to-1 ratio. This ratio is shown by the chart that I've drawn here. Imagine that I had a gas with a volume of 1 cubic meter, and I then increased the gas's volume to 2 cubic meters. If the pressure of our gas was originally at x, it would now be at 1/2 x. It would be half as much because the volume has doubled. Our next relationship is the one between the temperature and volume of a gas. In the late 1700s, Jacques Charles performed experiments on the relationship between these two variables. He found that as the temperature of a gas increases, so does its volume, and that this also happens in a 1-to-1 ratio. Again, it's super important for you to understand that the relationship between temperature and volume is in a ratio of 1-to-1. If we had a gas with a temperature of 300 Kelvin and we were to increase it to a temperature of 600 Kelvin, then the volume of our gas, originally at x, would also double, now at 2x. In the late 1700s, Amadeo Avogadro, the same guy who gave us that awesome number for the amount of molecules in a mole, hypothesized that equal volumes of gas at the same temperature and pressure contain the same number of molecules. So a box with 1 cubic meter of water vapor at standard temperature and pressure, and an identical box with 1 cubic meter of carbon dioxide at standard temperature and pressure have the same number of molecules in each box. This isn't a super intuitive concept, so let me try to explain it as best I can. The easiest way to think about this is to remember that in a gas, the distance between our actual molecules is vast. And so the actual size of the molecule doesn't really matter. What matters in a gas, and in this scenario, is the pressure in the box. Pressure is determined by the frequency and force at which molecules impact the walls of a container. So a molecule heading towards this wall and bouncing off of it would contribute to the pressure exerted by a gas. And so if all that matters is the number of molecules hitting the side of the container, and not the size of the molecules, because again, this value is negligible, then there must be an equal number of molecules per box if each box has the same pressure, volume, and temperature. I hope that makes a whole lot more sense. Let me know if it doesn't, and I will make a full dedicated video about this, although I'm pretty sure it's a topic that shows up later in the unit anyways, so I'll probably be going over it again. But going back to the topic at hand, Avogadro blessed us mere mortals with yet another beautiful conversion for his number. At standard temperature and pressure, 1 mole of gas will take up 22.4 liters of volume. And of course, we already know that this equals 6.023 times 10 to the 23rd molecules. We now have 3 different equations pertaining to gas. The first by Boyle, the second by Charles, and the third by Avogadro. What if we were able to combine these 3 equations with one another and create a super equation? That'd be a super fantastic thing to do. Worry not, for there is a Frenchman who has a solution, and like all Frenchmen, he has an extremely long name. In 1834, Benoit Paul Émile Clapeyron combined our 3 equations and came up with the ideal gas law, which reads PV equals nRT. Let's unpack this equation variable by variable. P stands for pressure, the frequency and force at which our gas molecules are hitting the walls of our container. V stands for volume, or the amount of space that the gas takes up. Our N value is our moles of gas. T is the temperature of our gas. And then lastly, R is the universal gas constant. Its exact value changes depending on which units you are using in your calculations, but all of its variations can be found on your AP Chemistry formula sheet. Another super important thing to realize about the gas constant is that your units matter. Pressure will either be in atmospheres or torr. Volume will always be in liters. Our moles of gas will obviously always be in moles. And our temperature will always be in Kelvin. Circling back to our universal gas constant, this could either have a value of 8.314 joules per mole Kelvin or 0.08206 liters atmosphere per mole Kelvin. Both of these are on your AP Chemistry formula sheet. Please don't memorize them. I mean, if you really want to, you can memorize them, but don't worry about it that much. One of the most important things to realize about our ideal gas law is that it keeps the validity of all our previous relationships intact. What would happen if we increased the pressure of our gas and we said that no variables could change their value except for volume? Well, to keep the equation true, volume would have to decrease. And because pressure and volume both have a leading 1 coefficient, this is in a 1-to-1 ratio. Imagine we increase volume, and we say that every other variable must stay the same except for temperature. For the equation to still read true, temperature must also increase. And again, this is a 1-to-1 ratio. You can go on and do this for every single variable in the ideal gas equation. Now that we're familiar with the ideal gas law, what can we even use it for? I'm not going to go through every instance of when we can use the ideal gas law, but you should be able to take up the base equation and solve for any missing variables when you are presented with the other values in a problem. That's just algebra. I'll give you 2 examples so you know what I mean. Our problem reads like so. A 2-liter container holds 0.082 moles of oxygen gas at 300 Kelvin. What is the pressure of our gas? Let's start by writing down our ideal gas constant. PV equals nRT. And let's fill in everything we know and don't know. P is the pressure of our gas. We don't know it because we're solving for it, so we leave that as such. V is the volume of our gas. We have 2.00 liters of volume. Super important thing I'm doing here. As you can see, I'm writing down the unit every time I replace a variable with a value. I do this to keep track of the units in my final answer, and that way you don't have to memorize the units that all of our answers are in. This will equal N, the number of moles of gas we have, which in this case is 0.082 moles, times R, our universal gas constant. In this case, it is going to be 0.08206 liters atmosphere per mole Kelvin. And the reason we're using this is because we were given our volume in liters. And then lastly, this will all be multiplied by our temperature, which is 300 Kelvin. I simply ran out of space, but all these 3 values on the right side of our equation are being multiplied. The first thing I'm going to do before going crazy with division is try to see what I can cross out. Here, I have a Kelvin in the numerator of a fraction, and here I have a Kelvin in the denominator of a fraction. These will cancel out with one another. Here, I have a moles, and here I have a mole in the denominator of a fraction. These will cancel out with one another. I have a liters on the left side of the equation and a liter on the right side of the equation. These will also cancel out with one another. All I'm doing here is some algebra to get rid of our units. You don't have to do it the way I'm doing, whatever works best for you. So if I now rewrite my equation, P equals 0.082 times 0.08206 atmospheres times 300 divided by 2.00. And as you can see, I took our 2.00 from the left side of the equation and I simply put it down there. All you have to do now is plug this into your calculator, and when rounded to 3 significant figures, you get a final answer of 1.01 atmospheres. Don't forget the unit down there. And how do I know that atmospheres is my unit? Well, look at that. It's the only one I even had left in my equation. So I hope that showed you how you can use the ideal gas law and why it's useful. Here's the second problem I'll be doing in this video, and it's a lot harder than the first one, so don't feel discouraged if you have no clue where to go from here. A 5-gram sample of an unknown gas is placed in a 2.5-liter container at 27 degrees Celsius and 0.850 atmospheres. What is the molar mass of this gas? You might be confused, but the simplest thing to do is just start by writing our equation. PV equals nRT. What are we even trying to do in this equation? Well, we have the grams of our unknown gas. And remember that the molar mass of a substance just equals the number of grams of that substance in 1 mole of that substance. And since I already have the number of grams and I'm looking for my molar mass, I'm going to find the number of moles of the substance I have, which is this N value in my ideal gas equation. So let's fill in what we know. The pressure is 0.850 atmospheres. The volume is 2.50 liters. And this will equal N, our number of moles, times our ideal gas constant. I'm going to use 0.08206 liter atmosphere per mole Kelvin again, since my initial pressure was given in atmospheres, and this one has atmospheres in it, and I want to cancel out my atmosphere, so that's why I'm going to do that. Then for my temperature, I'm given that we're at 27 degrees Celsius. But remember that my temperature always needs to be in Kelvin. To change Celsius to Kelvin, you just need to add 273 degrees Kelvin. So that would give me a final answer of 300 Kelvin. Now I'm going to cancel out some of the variables. I have an atmosphere here in the numerator on our left side and an atmosphere here in the numerator of our right side. Those will cancel out with one another. I have a Kelvin here in the numerator and a Kelvin here in the denominator. I will also cancel those out with one another. I have a liter here in the numerator and another liters here in the numerator. So those will cancel out with one another. And the only thing I'm left with is mole, which is good because that's what I'm trying to solve for anyways. So let's rearrange our equation. And now we just need to solve for our final answer. And we get that we have 0.086 moles of gas. And so now that we have our moles of gas, let's go back to this equation up here and plug in what we now know. The molar mass of this gas will equal our number of grams, which is 5 grams, divided by our number of moles, and we get a final answer of 58.1 grams per mole. And yes, that was a super hard problem, but I hope you kind of saw my thought process and you'd be able to tackle a similar one in the future. We have one last part of this video remaining, but we've already gone through so much, so if you've watched it all the way through by now, I implore you to take a 5-minute break and come back after. For the last part of this video, let's go over the assumptions we make about gases in order to use the ideal gas law and the deviations that can take place. The first assumption that we make about gases is that they take up no volume. We can do this because the size of a gas molecule is much smaller than the amount of space between gas molecules. The second thing we assume is that gases experience no intermolecular forces with one another. This is also fun to do because, again, gas molecules are so far apart from one another that they only come close when they collide, and so intermolecular forces rarely exist. But there are a few things that might happen in which our gas will deviate slightly from these laws. Number one, what if we increase the size of our molecule? Now our molecules are bigger, and so they will hit each other more often. Additionally, because the size of their electron clouds have increased, they are more polarizable, and thus experience stronger intermolecular forces with one another. When we increase the size of our molecules, we will begin to see deviations from the ideal gas law. Our answers will be slightly wrong. Luckily, as chemistry students, we can be knowledgeable of this, whilst also being blissfully ignorant in finding a true answer. So you'll never have to change the ideal gas law equation due to deviations from the law. You never have to change your answer. You just have to understand that deviations can occur and accept it for what it is. Number two, what if we increase the pressure of our gas? Our gas molecules are now crammed together, and they are much closer than normal. This will make them have intermolecular forces with one another more than normal, and make their size non-negligible, thus causing deviations in the ideal gas law. Lastly, what if we decrease the temperature of our gas? Molecules are now moving slower, which means that they will be passing one another slower. This makes intermolecular forces actually matter since they can exist for longer. This will result in a slight deviation in the ideal gas law. But again, you never have to change an answer even though you know a deviation exists. You just need to be aware of the fact that a deviation can occur. In this case, when we decrease the temperature of our gas. So increasing the size of our molecules, placing them at a very high pressure, or at a very low temperature will deviate gases away from ideal behavior. Therefore, we can decree the rule that gases will behave most ideally when molecules are small, at a high temperature, and a very low pressure. This is something you absolutely have to know. You also have to know the inverse. Our gases will deviate greatly from the law when our molecules are large, they are at a low temperature, and a high pressure. So if you ever come across a problem in chemistry which is asking which one of these gases will behave most ideally, just pick the smallest gas at the highest temperature and the lowest pressure. And with that being said, that's absolutely everything that you have to know about ideal gas law. If you're confused about any part of this, I recommend rewatching portions of the video. If it's still not making sense, take a break and come back after. This is an enormous topic with a lot of material, and I understand that it's challenging. Thank you for watching.